I'm Tom. I'm Tom Milner. I'm Director of Engineering at Tenable. My team has built a data platform over the last couple of years on top of Snowflake. And Neil here is Senior Engineer on my team. We both have been working on tuning Snowflake to within an inch of its life, really, in the last year. So we're here to share what we've learned in that experience, and hopefully you guys can take some of those lessons away. So first of all, what's Tenable? So Tenable is a cybersecurity company. We recently coined the phrase, or in the last year or so, we're kind of carving out a space more around exposure management. So helping customers manage their exposure, literally. So originally the company was set up by a Frenchman, Renaud de Raison. He wrote a piece of software when he was 17 called Nessus. Some people might be familiar with that. It's like a scanner. It looks for vulnerabilities on your laptops, on your servers. So that was our bread and butter for a long time, for a decade or more. But it only takes so far. Customers now, the infrastructure, the suite of assets that they have is a lot bigger. Cloud is here, people are here, logins. How people can get into your infrastructure is bigger. So we need to think bigger than just VM, than bigger than Nessus. So over the last couple of years, Tenable's been either building or buying different, what we would call scanners. So ways to basically scan more of your infrastructure. So one of those being web apps, like cloud security. We have identity security as well. So your AD account, often your AD account can be vulnerable, and that's the first stage for a hacker to get in and hit everything else that's in there. And obviously attack surface management, so everything that you have out there on the internet we have to do. So these are all individual point products that we call, so customers can buy licenses for each of them and use them to tailor to their individual needs there. And generally you have people who just work with one particular point product. But over the last couple of years, we've had a lot of customers coming to us and asking, okay, I want to see everything. I want to get a place where I can bring all that data into, and I want to get an overall view of the risks that I have, my exposure. How can I manage my exposure at a high level? So 2.5 years ago, we made the decision to build a data platform, get all this data in there, and we chose to go with Snowflake on that side. So so why did we choose Snowflake? There's a couple of reasons. The main one, though, it is a true cloud product. It does have separate storage and compute. For people not familiar with that, and I wasn't really familiar with how powerful that is until we started with it. I'd used other cloud data warehouses in the past, but using a cloud data warehouse that's built for the cloud with genuine separate storage and compute, just a very, Christian was saying that this morning, keep simplify. That is a very simple pattern, and it opens up a lot that we can do with it. So one thing that we do, you can see here in the diagram, so our team stops at the CIDIT database, data storage layer. We've built this platform, and other teams in Tenable come along and build applications on top of the platform. What we don't want to do is have noise or have cross contention on resources between different applications. So if somebody's running one query on a big application, that's going to hit somebody else in other architectures. With Snowflake, you give every application its own warehouse. We've been able to stick to extra small for all of our applications at the minute because we tune a lot in the pipeline, in the data model. We push a lot of costs left, if you will, into the data model so our customers can have a better experience and have quicker queries, shorter feedback cycles. So Snowflake lets us do that, and very simple, very easy, and it's been a good win there on that side. So just to go quickly through the agenda of what we're going to talk about here today. So before you start talking about performance, or if people are familiar with SLOs and SLIs, you need to have a baseline. You need to know where you're at and then make a target of where you're trying to get to. So I'll show you how Snowflake does that, how it lets you, there is lots of data in there, and there's lots of ways of getting that out and getting a clear picture of where you sit before you start any kind of performance tuning. And number two, I'm going to say micro-partitions a lot in this demo. Micro-partitions, they are key to performance in Snowflake. There's no getting around it. You really, really need to have a good understanding of micro-partitions and how you write data and read data, how micro-partitions can influence that. So that's going to be a key part of it. And then how you can influence micro-partitions with different patterns. So deferred merge, how you can use clustering, insert overwrites, order bys, go through a bit of that. And then we get into, Neil's going to take over from 3, but how you can build your data models. So do your aggregations. We try to use search optimization service. to reduce query compilation times. Compilation times, I'll talk about them in a minute, but how we can keep those down is a good part too. Join elimination, really, really powerful feature, like if it works for you. And then how we've worked with Unistore, how we tried it out and what we've learned, and we share that here. So, okay, so this is a P95 graph. We started this journey back in July, mid-July last year. We're building a new application that's going to be coming out very soon. It's pretty new for what we've done in Tenable, and it's going to be, we hope, game changer for our customers, giving them the insights that they need. But when we started using it in Snowflake last year, this was the average query speed. So of all the queries that were hitting it, we were getting over 17 seconds, which is not acceptable. Really not acceptable for our customers. It worked, it got you the data back, but you're sitting there looking at a spinny wheel for a while, so not good. So working with product managers and other teams, they gave us some targets that we had to hit, and we went for it. So we actually went from over 17.5 seconds to, this was in April, to 1 second. 1.1, kind of, we're averaging, this is P95 graph, and that stayed steady. To be honest, we've kind of hit a floor there, and we can't break through it. But it's been good. We've been kind of able to keep it down there because we've got the fundamentals right now. People can throw more queries at it, or more complicated queries, and it seems to work pretty good. So this is key. So get your measure, get your baseline. Where are you at now? Monitor your baseline. So every day we've got reports that come out. We've got a notification set up that says, okay, this is starting to go out of kilter. Someone needs to go look at it. That's part of our job as the platform. If query speeds for certain applications start to go up or down, we go in, we investigate, we try to see what's happening. And then we adapt. So either that's a change on the customer's end, which we're not finding too much now. We work with our customers on a daily basis and teaching them about the data model and how best to get the performance out of the data model. So basically, and then maybe like we had a case in February where there was a change on the Snowflake side that caused provisioning time to go up. So we go to Snowflake, we say something's not right here, and they can adapt for us on that side. So constantly monitoring and then adapting if you need to, and then you get a new baseline, because it may be a new use case that does increase or decrease your baseline, and you can't do much about that. So you change your baseline. I won't go through this, but if the slides get shared after, you should have this query. But this is showing, it's all off query history. And basically, it's a query that we run and that we've built a monitor off. So there is loads of data in Snowflake already. I know they've announced a lot of observability stuff, but there is loads of data in there for you to use and get at. So it's really good. So the key fields out of query history that are worth looking at are, so elapsed time, that's the time that took the query to run. Okay? Overall, that's how long it took. Compilation time. So when you send a query to Snowflake, it spends some time looking at that query. Is it in cache? Okay, has the cache changed? Has the data changed since it's in cache type of thing? And it'll invalidate the cache. Okay, what micro-partitions do I need to go and look up to get this data? Which micro-partitions do I need to open up to get the rows that are looked for in this data? And then back out. So compilation time takes time. We've seen seconds, basically, just for Snowflake to work out a query and what to do with it before it even starts to do anything. Queue provisioning time, so if you have a warehouse up already, this will be low. If you don't have a warehouse up already to run your query, that would be the time. So like if you're only running 1 or 2 queries a day, queue provisioning time will be high. If your auto suspend is really low and the warehouse is going offline pretty quick, that will be high as well. So it's a good balance there. You need to work that one out. It just starts to go high. You want to look at how you're provisioning your warehouses and what that means. And then execution time is actually the time that runs the query. So that's the one you'd have most. It does take the longest, I could say that, yeah. It is the biggest chunk of the elapsed time, but it's the one you have the most influence over and the one you can affect the most. So query load percent. So one thing you'd want to look out for, like you don't want to be really measuring the time. The queries in cache are great. Like you really, like if you can be serving queries off the Snowflake cache, that's really good. It's 100 milliseconds or maybe a little bit more. So you can get a lot of queries coming out of cache. That's really good. But overall, I found I want to keep that out of my measure because I want to see what the true time it is of, the true time it's taken for a query to run, and that's what I can influence. So you might want to take that into account. And then query parameterized hash, that was a new feature that came out last year. That's been really, really good. So like you can basically go in and group all your queries together. You can know without the parameter, basically it's a hash without the parameters in the query, so you can kind of see what queries have been run more often and which ones you need to go in and tackle. So first thing I would do if I see the query, the SLI start to go up, I would kind of go and look at, I'd go and group by parameterized query hash, try to find the queries that are the highest and work down from there. So it's really good. Yeah, that's the query I use for parameterized query hash as well. Okay, so I mentioned micro-partitions. These are key, fundamentally key to understanding how you can get performance out of Snowflake. I was about a year into my journey with Snowflake, and I'd heard about micro-partitions. I thought they were just kind of, we were treating the storage like a black box, just write the data, not really thinking about it too much. It's a big mistake. Started looking at micro-partitions, started to understand how we can get more out of this. So, in summary, if people are familiar with S3 or object storage or anything like that, like a micro-partition is a file or is an object in S3. That's the most fundamental way I can talk about it. So, and when you think about that, an object in S3 is immutable. Once it's written, it cannot be rewritten, it cannot be updated. If you change an object in S3, you're writing a new object. Take the example of if an object contains 1,000 rows, that object in S3 has 1,000 of those rows. If you change one of those rows in that table, or one of those 1,000 rows, whether you delete it, whether you update it, Snowflake has to basically write a whole new object. So say you've deleted one, it'll write a new object with the other 999. That's why it takes time. Yeah. So it's not like a file-based system, it's an object-based system. And understanding that is kind of, it's a good mental model to have. Like I said, they're immutable. Once written, they can't be updated. Yeah, so that, and then micro-partitions are not shared between tables. So like one micro-partition would only be used by one, would only map to one table. Obviously a table can have multiple micro-partitions, but they don't get shared out like that. So, yeah, Snowflake stores metadata. So when I talked about query compilation times, that's Snowflake going, okay, these are the rows that is needed to fulfill this query. Where do those rows sit in a micro-partition? And it stores data about the micro-partition in the cloud services layer. So it'll have a range in there. It's columnar store. So it'll say ranges 1 to 10, or in this micro-partition has rows 1 to 10 type of thing. So it knows then, it's not storing details about every row in the micro-partition. It just does it at a kind of a range level. So yeah, so you really need to understand how micro-partitions work. So yeah, this is a diagram from Snowflake's documentation. So you have your logical structure, there's your table with all the nice rows, but in the background, they can be split across multiple micro-partitions. So as I said, when the cloud services layer is trying to address a query, it'll know, okay, I need to go 4 is in micro-partition 1, and 3 is in micro-partition 4. So it knows where to go and get them. But it has to go then and open up all those objects in S3 to crank it out. So what you want to do is limit the number of micro-partitions that are needed to address a query. So, okay, so steps to control it. Write your data to match how you want to retrieve it. It's simple, like in any data system, like whether it's SQL Server, or Oracle, or S3, or Hadoop, or Snowflake, how you write your data, how you index your data influences how quickly you can retrieve it. So using a key field that basically you know you're always going to be querying on. Tenable is a multi-tenant system. So we would have data from lots of different customers sitting in the same tables. We use that key then in every query. So it makes sense for us to basically group our data by that key. If you have time series data, maybe it makes sense for you to group that by a derived key, maybe like year, month, day, or something like that. And that means your data is getting ordered in the way you need to retrieve it. And that means you need to access less micro-partitions to get the data back. Yeah, so there's a number of ways of how you can control micro-partitions. Easiest one is auto-clustering. Just add a cluster key to the table. Snowflake will take care of the clustering for you. So it works pretty well. We found it's very good for small tables. It's very good for tables that don't change much. But if you've got a large table that's getting a lot of updates, auto-clustering can be expensive. So you may not want to go that route. Okay, The other option you can do then, really for any insert, you should be using an order by. If you don't use an order by, Snowflake's going to pepper all those rows across multiple different micro-partitions. So this tenant key that I said that we use, if I don't order my inserts by tenant key, that's going to scatter all those rows for that tenant into lots of different micro-partitions. If I order it by tenant ID, it's going to create a micro-partition for that tenant. Maybe depends on how much rows you have. It could create multiple micro-partitions, could put multiple tenants into the same micro-partition, but when the query comes in to retrieve that data, it knows, okay, based on the range, I can go to this micro-partition and get all the data that I need. So that's why order by is really, really important. For some of our mid-sized tables, you could do an insert overwrite with an order by. So basically, you're truncating and rewriting the table, all the data in the table, again, just to maintain a really good micro-partition profile by that tenant ID that we do, or whatever key makes sense in your use case. It sounds mad to rewrite the whole table every time, but it's actually not that expensive. And as I said, we're pushing our costs left so our customers can have a better user experience and lower feedback times. So that works well. Number 4, avoid the merge pattern. It's like you cannot do an order by with a merge statement. So if you try to do a merge and you're doing an insert and an update, you can't add an order by to your insert. So we've basically broken them in two anytime we've had them. We do a separate update, we do a separate insert, whichever way makes sense in that order. So I would avoid the merge statement fully. I don't know, it could be a feature for Snowflake to add an order by to merge statement. I don't see why, but it's not there. Yeah. And then deferred merge pattern, I'll go through that next. So this was a pattern that Snowflake introduced us to, and it works pretty well. If you've got a very large table, lots of transactions coming in, you may want to consider a deferred merge. So how deferred merge works is you basically create 2 tables, one with hot data, one with cold data. Hot data is the new data that's coming in a certain time period. Like for certain tables, we use 24 hours. For other tables, we use 3 hours. It all depends. And then when number 2 comes along, you've got enough data, enough change data in the hot data to write good-sized micro-partitions down to 2. So you're not going to do an insert overwrite here. Like this is too big for insert overwrite. This is like you want to chunk up your data, so you've got micro-partitions in there already by the key that you need, but now you're going to add more micro-partitions, but they'll be ordered by that same key. And then to make sure your customer, you only want to have one endpoint. You don't want to be doing a union all separately. So you put a view over both tables, and what you're doing, the view would have to have some smarts to basically exclude rows from the cold data that's not in the hot data. No, that's in the hot data. Exclude cold rows that are in that data. So that's one thing that can mess up the compiler a bit if your queries are getting too complicated in the joins. You're joining into a view that's doing maybe we were using what were we using? Not exists, I think. We were using not in the view, and that was not working really well. So we actually changed to where not exists, and that worked a lot better. I'm not 100% sure why, but we were getting better in query plans in that case. So having the view there, you just need to be careful with it, how you use it, just monitor again and measure. Yeah, so that's one area that like you are still pushing a bit more onto your customer, but it's worth it in terms of if you've got you can't just have them at a highly transactional table. It's just not queryable. Okay. Yep. I got time.
Yeah, it's cool.
Hand you over to Neil. He's going to take you through the rest of it.
Thank you, Tom. Yeah, hi everyone. So as Tom mentioned, we have our applications, in particular this one, Tenable one, where we have sort of asset inventory information. It's querying directly against Snowflake, real-time queries. So here's an example of one of the pages, and it's returning row-level data, but we aggregating certain values at the row level. So initially, the initial implementation of that, we had all the logic, built in the real-time queries. So there was complex, additional joins, filters, group by clauses, and we're finding having all that logic built in there, it was, not performing very well to handle the aggregations, and in fact, it is causing very high read costs. In fact, our SLA team had set very, obviously set some tight SLA times. And we're badly breaking them. You can see there, with the having all the additional logic in the real-time queries. So what we did is we decided to move that right into pre-compute. So we built purpose-built fact tables, and we materialized the aggregations into those fact tables so that it's all pre-computed. This eliminated the need for joins and all that complex logic at the real time. So we had the data coming in by streams. So we had streams on the source table essentially. So we only recomputed when there was changes to the source data. So we weren't recomputing the whole lot every time. It'd be costly, etc. So if some of the source data changed, we'd just recompute for that source data for that particular client key, and then just save it back to the fact table. So as Tom mentioned, we have this multi-tenant key. We classified that key in these fact tables as well, and that serves two purposes because that's using every single every query we have on the front end. It meant that the queries were optimized. We were able to get the data quickly because we were filtering on that key. Additionally, on the transforms, we were able to then use that to do sort of a partition switching logic. Essentially, we were just, if a particular container or a tenant key was modified, we'd delete out that whole container or that whole tenant. That eliminated all those micro-partitions for that particular client. And then we just reinsert the whole recomputed values at the end. So this, optimized kept it optimized for the query. And these were all scheduled with tasks, which meant we could control the latency. We could make it, if we want to run a 5-minute schedule or an hour schedule, we could control it with tasks. So this at the bottom is just a very simple overview of what we did. We had the streams, looking for changes, picking up changes. If a change came through for a particular tenant, we'd delete that out. Delete out the containers for that, or the partitions for that. Reinsert the aggregated values, and then just optimize for that. So after all the work that Tom mentioned on the micro-partitions and this aggregation stuff, the pre-computing the aggregations, we found we actually were well within the SLAs, but there was a few queries we thought, let's see if we can get faster. So obviously we wanted to try out a few things. So the one thing we wanted to try is search optimization service. So those who don't know search optimization service, it's very good for point lookup queries for highly selective values. So if you've got sort of 100 to 200,000 distinct values, it's ideal for that kind of scenario. If your query is running over 1 second, it's good for that. Joins with filters, it's not good for the joins itself, but it's good for the filters and the joins. I think the joins functionality is still coming with Snowflake. It's good for variant columns and something we weren't doing a lot of, but it's also good for query regex expressions. So what we did is we had a particular case with a few fact tables of dimension where it wasn't, sorry, let me just go to the next thing. So what we did is just create a POC on just about 7 odd tables, a combination of fact and dimension tables. So our key takeaways from search optimization service was, I'll just call it SOS for short, tongue twister. There's a great feature for cost estimation, which is a simple query, and it returns information about your build costs, your storage costs, and maintenance costs. So at least you can get an idea of what it's going to cost you. That's not exactly what the actual values we saw, but at least it gives you an idea of what to expect. It's very easy to implement. You can see it's a simple alter table, add search optimization on equality, and you specify the columns you want. So a very straightforward implementation. We did that across seven odd tables. And this is the performance. You can't see the color so well here, but what we found is that it was sort of the standard tables and search optimization tables were very close in performance. In some cases, the SOS was quicker, and whereas the standard tables in some cases were quicker, but within like milliseconds of each other. And so as we dug further into it and looked at the execution plans, we noticed that they were doing very similar partition elimination. So, which it was sort of based, because of the amount of work we spent doing on the clustering, we were actually not getting much value from the SOS because it was the partition elimination was basically the same, the partition pruning. Also, one other factor we had was that we were using insert overwrite a lot on a lot of our tables. And that's not ideal for search optimization service because of the costs associated. If you're using insert overwrite, you basically it's recreating that table every time or reinserting everything. and then just rebuild the search optimization indexes. So that's not ideal for SOS. So that's why we didn't really go full. We didn't go ahead with this in production, basically, and also because we were getting equivalent value from the clustering itself on standard tables. The next thing we then wanted to do is, well, when we first implemented the data model, we were trying to keep things simple, and we created, for our dimensions, for example, we created a super dimension with sub dimensions, but it meant that we were having to join. Once we started implementing queries in the front end, we were joining between these, and obviously with all the joins, that is causing a lot of cost. So we found that by denormalizing the model simply, it just, it is with the standard tables, it's column store. You can go with wide tables. There's no reason why not to. So we just combine those multiple dimensions, single dimension into one single table. In fact, it's one dimension table is 190 columns wide, and it doesn't matter that there's null values for some of the fields if necessary. But by doing that, we eliminated a bunch of joins, and that just really made a difference for the query optimization. Also, we noticed as well that if you joining tables of different grain, that's also not ideal. So again, you can try and denormalize we did anyway, you denormalize some of those tables into one table and at the same grain. Yeah, another thing we found is we have a client library, which is all the applications use, where we have basically views that the clients consume, clients applications. And initially, when we started the project, we built some of the business logic into those client views, which obviously meant that there was complexity there, and they were slow. Not slow, but they weren't as optimal. So we then decided to, either move some of the pre-compute left, and that really helped, or put some of the business logic into the applications or services themselves, and that really made a difference. We just kept the views as simple as possible, straightforward selects of the tables, and then the logic could be handled in the application, or we did a pre-compute to get the data into the tables, and that really made a big difference as well. And then the rely keyword, which Tom mentioned earlier, this is a very cool feature. So many of you will know that the constraints on the standard tables are not enforced. But if you apply the rely keyword, it helps the optimizer. So there's an example here where we put a rely on a foreign key to a dimension table. And in the join there itself, it can actually just eliminate the join to the dimension, because the asset keys are already in the fact table. So the optimizer knows it doesn't need to look at the join to the dimension, just eliminates the join together, and therefore it's a quick query. So this is a very nice feature. We put it across all our queries, or our tables, sorry. And then as Unistore became available, it was a very exciting prospect for us, and I think it's got great big potential for certain use cases. So for those of you who are not familiar with this as well, I just thought it'd be good to do a comparison, because probably most people are familiar with the standard tables. So while standard tables are columnar store, hybrid tables are row-oriented storage, and they have a secondary columnar storage. So if you run a query against a hybrid table, the optimizer knows, based on the type of query it is, whether it can go to the row storage and collect the data, or whether it'll go to the column store, and obviously therefore it's it optimizes the return of the data. Standard tables are very good for analytical type use cases, for aggregations and that kind of thing, whereas hybrid tables are good for transaction type single row use cases. As you know, I'm sure you know that standard tables, you don't have indexes at all, which makes it simple, and except for the clustering key, is not much. The performance is good just with the clustering key. Whereas with hybrid tables, you can index them, and you can create secondary indexes as well. And also on the standard tables, constraints are not enforced, as I mentioned before, but hybrid tables, your primary keys are enforced for uniqueness, as well as the foreign keys are enforced for referential integrity. And the last thing is that standard tables are optimized for large analytical workloads, whereas the hybrid tables are for short-running, low latency, high throughput, read and writes kind of queries. So the positive things we took out of Unistore was that it was very easy to convert, particularly in terms of the signatures in the client library. There was no need to change the views whatsoever because you're not changing the table names, views, etc., column names, etc. Even in the table changes, it's just a simple change to the DDL, maybe to your referential integrity, but otherwise not a big change there either. The big difference is, as I mentioned before, that the foreign keys are enforced. And you can only do foreign keys hybrid to hybrid. You can't do a hybrid to standard table. And then, of course, primary keys are enforced. Now, the enforcement of foreign and unique keys we found is useful for data integrity, so it definitely could help with data quality. So we did a POC, took a particular case where it wasn't a highly concurrent use case, but we had a particular table, dimension table, and an effect table associated to it that had a 5-minute latency. We're updating every 5 minutes, so we thought, let's try this and see if we can get a better performance on that as well. So the output of that was that we found that on updates, the hybrid tables were definitely faster. You can see there it was a 0.5 milliseconds versus 0.9. In terms of queries, we weren't seeing a significant advantage over the standard tables, which, as we mentioned before, have been highly optimized. We spent a lot of time doing that. They are very much similar in terms of performance, with a couple of milliseconds out the hybrid tables. But what we did notice is that when we delve further into it, that the execution times on the hybrid tables was quicker, whereas the compilation times were a bit slower. So we're actually working with Snowflake to see if we can bring down compilation times. If we can bring down the compilation times, these would be probably performing quicker than the standard table queries. And the ETLs were similar. What we did find is that because of the referential integrity, we had to add in, we had to add additional logic into the ETLs to handle because whereas before we could just say insert, delete and insert into table, now you couldn't do that because it's referencing other tables, so you had to handle that in ETLs. So there's a slight delay in that, in the times for that. So for hybrid tables, there are a few limitations currently. Currently, the public preview in select AWS sites. So if you were to go ahead at hybrid tables, you have to think of something smart on the CI/CD side or sort of branch your deployments. If you're going to Azure DB, for example, you'd have to deploy standard tables, whereas if you're going to AWS, then use the hybrid table. So you'd have to think of something smart there. And clustering keys are not currently supported. There's a 500 gigabyte storage limit and a 1,000 transactions per second limit. However, if you talk to your account team, they can apparently raise those limits as well. And there's some minor secondary index limitations, like you can't create secondary indexes on variant columns, for example, and you have to recreate an index if you make changes to it, some small things like that. Then the one big factor for us also was the referential integrity versus eventual consistency, because with clustered tables, we don't enforcement of primary keys and foreign keys. We were relying on eventual consistency, so there's no dependency in the ETLs on the data being available in the different tables. But whereas with hybrid tables, then you have to make sure your DAGs are, your orders are correct, and that you get the data, say for example, in the dimension table before you load the fact table and that kind of stuff. So it's an important factor when you're going with hybrid tables. And then there are some additional costs associated with hybrid tables. Firstly, there's the storage. Storage costs are slightly higher than the standard tables. There's a gigabyte per gigabyte cost on a monthly basis for hybrid tables. The virtual warehouses are the same whether you're querying. The cost is the same whether you're querying standard or hybrid tables. There's no impact there. And in order to query the hybrid tables, there's serverless function to retrieve the data called hybrid table request, and there's additional cost for that as well. Lastly, in terms of monitoring, there's the standard queries the standard views have got some additional columns that will help for monitoring the standard tables. And in addition to that, Snowflake have provided additional views like hybrid table views and hybrid table usage history, which allows you to monitor the storage of your hybrid tables. Also, because of the high concurrency of hybrid tables, you need to be looking at things like show transactions, show locks, and lock wait histories. Also, there's a new feature, which is the private preview, which is a group query history. It's a nice UI which you can actually view, which are useful for hybrid tables because you can see the, you can see a large amount of queries aggregated over a period of time. So in summary, this, all these, we've had a very good journey. We learned a lot through the different features and what we've done in the past, 2 years on Snowflake. And it all depends on where you are in your journey. If you're starting out and you have a highly concurrent environment, you may want looking at hybrid tables. If you've got standard tables and you're looking to improve, what Tom's mentioned in terms of micro-partitions and stuff, that's a very important things to look at and rely keywords. So yeah, there's lots of things, search optimization service. So there's lots of ways to improve your performance based on the journey, where you are in your journey with Snowflake. That's it. Thank you.